Alright, so far we had studied the differential amplifiers. Okay. So till the previous lectures we had seen the differential amplifiers or differential pair using the two transistors connected in parallel. Okay. So now let us talk about the difference amplifier. I mean it is same differential pair. Okay. So we want to talk about the differential pair or difference amplifier. Okay. So let us say the same differential pair that we have studied so far, so that can be represented by this symbol, let us say. Okay. So it has two inputs, differential inputs, and an output, standard output over here. Okay. Now we had seen earlier that our differential pair, so that was sensitive to the difference in the input voltages, and it was insensitive to what was common to the two inputs. Okay. That is, if these two inputs are different, then only we saw some output, otherwise the output was zero. That is, if V in 1 is V in 2 equal to V in 2, then output is 0. If there is a difference between V in 1 and V in 2, then only output would be present. Okay. So one can write this differential input as V in 1 minus V in 2. Okay. Similarly, the common mode input one can write as V in 1 plus V in 2 by 2, that is the average of these two. Okay. Now the output of this difference amplifier will contain the differential mode input, I mean the output due to differential mode input also and common mode input also. Okay. And we had earlier studied about these two gains, differential mode gain and common mode gain. Okay. So ideally we want this common mode gain to be 0, okay, so that CMRR can be high and so that there is no noise present in the output. Okay. But if this also is present, that is it is not 0, so then it has to be included in the output apart from this differential mode gain. So the output of this amplifier or this difference pair or difference amplifier can be written in terms of both differential mode gain and common mode gain. Okay. So that is differential mode gain multiplied by the differential input V in 1 minus V in 2. Similarly, common mode gain multiplied by the common mode input, which is the average of these two inputs, V in 1 plus V in 2 by 2. Okay. Now we had commented earlier that I want my differential mode gain to be much greater than common mode gain. In fact, common mode gain I want to be equal to 0, so that my common mode rejection ratio, this can be equal to very large or infinite. So this is possible when common mode gain is 0. Okay. So otherwise it may not be infinite. If it is having some finite value, so that means output is corrupted by noise. Okay. So if common mode gain is not 0, so that means there is some noise or some undesirable output present. Okay. So if CMRR is infinity, then that means the noise is not present in the output. Now let us talk about OPAMPs, okay, that is operational amplifiers. Now this OPAMP is a special kind of difference amplifier, that is the same difference amplifier that we have studied so far by using two transistors in parallel. This OPAMP is also this difference amplifier, but it is a little special in the sense that it has these properties, that is it has a very high differential mode gain. So differential mode gain is very high. Okay. Common mode rejection ratio is also very high. Then the input resistance or input impedance, so this is also very high, and the output resistance or output impedance is low, very low. Okay. And if we talk about the ideal properties of an operational amplifier, so then we would like that these properties, that is differential mode gain, should be infinite, CMRR should also be infinity, input impedance infinite, and output impedance 0. So these are the ideal properties of OPAMP. Okay. Now to match these properties, so obviously this circuit, that is this difference pair, has to be modified, right? So that is why, I mean, that is how it becomes a special kind of difference amplifier. Okay. If you modify this circuit to match these properties, then this operational amplifier can be called as a special kind of difference amplifier with these properties. Okay. Now to match this property, we'll talk about the circuit inside this op-amp. Before that, let us comment on this CMRR again. We had seen that CMRR can be written as the differential mode gain divided by the common mode gain. Okay. Or in terms of dB, I can write 20 log mod of AD by mod of AC. Okay. And we had also seen that the output of this op-amp can be written in terms of both differential mode gain and common mode gain as this much. Now this can further be simplified, that is this V0 can be further simplified to this relation, where this 1 by CMRR term is coming from here, that is AC by AD. So AC by AD is 1 by CMRR from here, that is put in this equation. So you get final V0 of op-amp in terms of the differential mode gain, common mode gain, the differential mode input and common mode input. Now let us utilize this relation to solve a problem over here. Now in this problem we have been given an op-amp and with input voltages of the op-amp being these, and it has a differential gain of 4000. CMRR is also given to me as 1000, and we are supposed to find out the output voltage of this op-amp. Okay. So for finding out the output voltage, I'll simply use the previous equation, that is this equation over here. So I'll copy this equation here, right, and let us see. So this equation is copied, V0 is this much. Okay. Now in this relation, the differential mode gain is known to me, CMRR is also known to me, and these things have to be found, VD and VC. Okay, that is differential mode input, so which can be written as VI1 minus VI2. So 150 minus 140 is 10 microvolts. Similarly, the common mode input, that is the average of these two inputs, which is 150 plus 140 divided by 2 is 145 microvolts. So I plug in all these values into this equation. Now V0 is found as 45.8 millivolts. Okay. So the input was very low in microvolts and the output we are getting high output, okay, in millivolts. So this is possible because of this gain, okay, of this op-amp, which is 4000 currently over here. Okay. So the output is decided by the gain of this op-amp, okay, in this open loop configuration. Now in your lab you will find an integrated circuit, okay, for this op-amp, which is the number of the IC is LM741, which is an operational amplifier integrated circuit. So this integrated circuit op-amp, it has 8 pins, 1 2 3 4 5 6 7 8. Okay. So now for example 2 and 3 are inverting and non-inverting inputs. Okay. So in the op-amp symbol one can mark 2 as inverting and 3 is non-inverting input. 6 is output. Okay. And 7 and 4 are plus minus VCC. So 7 and 4 are plus minus VCC. Okay. So this negative here means it's an inverting terminal, okay, and this positive here means it's a non-inverting terminal. Okay. Then in the data sheet of this op-amp you will find input impedance, voltage gain, large signal voltage gain, common mode rejection ratio, and many other parameters are mentioned. Okay. Now as I said that op-amp is a special kind of difference amplifier. Okay, so that is the properties of this op-amp are special in the sense it has high or infinite gain, right? So gain was infinite and input impedance was also infinite, output impedance 0, and CMRR we had said that this has to also be infinite. So to match all these properties one has to modify our differential pair to result into op-amp with these properties. Okay. So that is, now my circuit becomes a complex circuit. So this op-amp is a complicated circuit which contains several transistors and resistors just to match these ideal properties parameters. Okay. So you will find that in an op-amp there is a difference amplifier also present. Okay. So for example This may be a difference amplifier. Then you have several current mirrors. For example, this is a current mirror 1, okay, 2, okay, and so on. So it is a complicated circuit of transistors and resistors to match these properties. Okay. Now let us draw a simple equivalent circuit model of this op-amp. Right? So for this op-amp, a simple equivalent circuit model could be this, okay, where at the input the differential inputs are present, okay, and the differential input Vi, so this drops across the input impedance. Okay. So input impedance here is Ri, okay, and this differential input drop across this input impedance of this op-amp. Okay. And we had already commented that input impedance should be very high or infinite. So let us say that this op-amp is not ideal, but it is near to ideal. Okay. So that we can assume that Ri is input impedance is very high. Okay. So if I assume input impedance very high, then 1 mega ohm, let us say that input impedance of this op-amp. Okay. Then on the output side of this equivalent circuit, we have the output impedance. Okay. Output impedance we had assumed for an ideal op-amp it was 0. Okay. But here let us say it is very low because this amplifier is op-amp is not ideal, it is near to ideal. So it is very low, let us say. So that very low number is, let us say that output impedance is 10 ohms. Okay. So output impedance is 10 ohm, input impedance is 1 mega ohms. Okay. Now at the output we have open loop gain multiplied by the differential input, right, appearing here, the open loop gain multiplied by the differential input. Okay. So the gain of this op-amp that I have been saying that it should be infinite, okay, if it is an ideal op-amp. Okay. So that means I am concerned about the open loop gain. So open loop gain should be infinite or very high. Okay. So I'll write open loop gain. So this is AOL is open loop gain. Okay. So this should be very high. So let us say that the open loop gain is somewhere around 10 to the power 5. Okay. Open loop gain is 10 to the power 5 for this op-amp, and let us also assume that it has a very high CMRR. Okay. So the equivalent circuit of a op-amp can be represented by this equivalent circuit model. Okay. So in this equivalent circuit we understand that the output voltage V0, so that will be equal to the open loop gain multiplied by the input voltage. Okay. So whatever the differential input are present, the output will be equal to the differential input, that is Vi1 minus Vi2 multiplied by the open loop gain. Okay. So the open loop gain we have already assumed that it is very high, 10 to the power 5. Okay. And imagine if input Vi, or maybe let us talk about it little bit later. Okay. So if open loop gain is 10 to the power 5, and in the case when open loop gain is infinite, okay, so that does not mean that my output should also be infinite. Okay. So if I say that this open loop gain is infinite, so that does not mean that output can also be infinite. Okay. But this output cannot be infinite. Obviously it has to saturate at some value. So that value is VCC plus and minus VCC. So that is the maximum output voltage that can be achieved by this op-amp is plus minus VCC. Okay, so whether in open loop configuration or whether in closed loop configuration. Okay, so one cannot achieve an infinite voltage. Okay. So the output will be saturated to plus minus VCC. Okay. Or if I try to draw the output versus input, so if the input is increasing, so obviously the output should increase up to this point only. Okay. After that it saturates to plus VCC and minus VCC. Okay, or we call that op-amp is saturated, okay, because the output is saturated to plus minus VCC power supply. Now we said that this plus indicates it's a non-inverting terminal, okay, and this minus indicates it's a inverting terminal. Okay, so non-inverting terminal here means that whatever you apply at the input, you will get at the output you will get an amplified version with same phase. That is, magnitude of the output can be different, but the phase will be same. Okay. Similarly, if it's an inverting input is applied, then the output will be, magnitude may be different, raised up large because of the gain, but the output and input will be out of phase. Okay. So that is why this is called inverting, because output is out of phase with the input. It is called non-inverting plus 1 terminal because the output is in phase with the input. Okay. So let us say that to the non-inverting terminal some input is applied. Okay. And let us indicate, so let us say that non-inverting terminal the input is applied and the other terminal is grounded. Okay. So in this case the output is in phase with input. Okay. So it is in phase with input, so that is why we say we indicate this by positive on both input and output. Output is positive means output is in phase with input. Okay. Similarly, if I try to apply input signal on the inverting terminal. Okay. So input signal now is applied to the inverting terminal. Okay. Now in this case, a negative output here would mean that the output is out of phase with input. Okay. That is, you have applied an input signal to the non-inverting terminal. So the output may have a different magnitude, a larger magnitude, but it will be out of phase with the input. So to represent out of phase, we use negative over here at the output. So output is negative in this configuration, which is inverting. Okay. The output is negative, so that means output is out of phase with the input. And in this configuration, which is non-inverting, okay, the output is positive, so that means output is in phase with the input. Okay. So output is in phase means, let us say that this is my input. Okay. So output will be in phase, but it may have a larger magnitude. Okay. Similarly, if my input here is this, the output will be out of phase, so that means this is 180-degree out of phase. Right? It may have a larger magnitude, but it is out of phase with the input. Okay. Now let us say that I have this signal Vs, which is 1 millivolt sine omega t, okay, and we want to amplify this signal. Okay. So can we amplify this signal using this op-amp? Okay. So if I try to use this op-amp by simply connecting this input signal on V1, let us say, so that is Vs is applied to the non-inverting terminal, okay, and the other terminal is grounded. So can we amplify this signal? Okay. So we had already commented earlier that my output, okay, that is the output of the op-amp is equal to the open loop gain multiplied by the differential input. Okay. So the other input is grounded to 0 and this non-inverting terminal is being fed with this Vs, which is 1 millivolt sine omega t. So can we amplify this using this configuration? Okay. So let us understand. The output is this much, okay, and the open loop gain we had earlier written that it is 10 to the power 5. Okay. Open loop gain we had considered it's high, it's 10 to the power 5, let us say. Yeah, we are assuming Ideally it should be infinite, but let us say it is finite. It is not an ideal op-amp, but the gain is very high. Let us say open loop gain is, let us say, 10 to the power 5, right? Ideally it should be infinite, but it is, let us say, 10 to the power 5. Okay, so we use this equation to find out the gain, that is V naught is open loop gain, that is 10 to the power 5 multiplied by Vs, which is 1 millivolt sine omega t. Okay, so 1 millivolt, that is 1 into 10 to the power minus 3 volts sine omega t. So that is 10 to the power minus 3 sine omega t. So this is the output, so which is equal to how much? 10 to the power 2 sine omega t. Okay, so this is my output. So 10 to the power 2 here means 100. So that means the magnitude of my output is 100 volts. Okay. So is it possible, when we are saying that we are only applying plus minus VCC of plus 12 volts and minus 12 volts? Okay, so is it possible? Okay. Because op-amp voltage is limited to only plus minus VCC. So that means we cannot amplify this signal to 100 volts. Okay. Then how do we amplify this signal? Okay, because open loop gain is 10 to the power 5 large. So how do I utilize this op-amp for amplifying this signal? Okay. The output cannot be 100 millivolt. It will be saturated to plus minus 12 volts. Okay. So how do we amplify this signal then? Can we attenuate the signal to 0.1 millivolt and then amplify? That is, can we reduce this magnitude to 0.1 millivolts and then amplify? Okay. A better solution would be to use the op-amp in closed loop configuration. Okay. So a better solution is to use this op-amp in closed loop configuration, that is, the output, some part of output is now fed back to the input via this resistor. So you are using these two resistances R1 and R2. Okay. And the loop between output and input is closed over here by this feedback resistor. Okay. Okay. Now if I use this closed loop configuration, then I can control this output. Otherwise the output is uncontrollable, we had seen. Okay. So for example, in this configuration, which is open loop, or maybe here we had seen. So this was an example of open loop configuration. Okay. So I'll write over here that this was open loop configuration, and we had seen that the output is uncontrolled here. Okay. 100 volts, so which cannot be achieved. So to amplify this signal, I have to utilize the op-amp in a closed loop configuration. In fact, the op-amp is never used in open loop configuration. Op-amp is never used in open loop configuration. So op-amp is always used in closed loop configuration by considering these resistances feedback from output to input. Okay. Now here the output is controlled by these two resistances. Now again here you will find this output cannot be more than plus minus VCC. Okay. So output, the maximum output that can be achieved by op-amp, whether in closed loop or open loop configuration, is always equal to the power supply values, that is plus minus VCC. Okay. But here the gain is controlled by these two resistances. So the gain, or V naught, is a function of these two resistance R2 and R1. So by changing the value of these two resistances, one can change the output of this op-amp. Okay. Or the gain of this amplifier op-amp can be set now by these two resistances. Okay. Now the output is fed back to the input here. Okay. So this feedback signal which is coming from the output, if it helps the input voltage, then we call that it is a positive feedback. Okay. Okay, that is the feedback signal if it helps the input voltage. Okay. That is, if my feedback signal is added to the input before being applied to the terminals of the op-amp, we call it a positive feedback. Okay. Otherwise it is negative. In this case it's a negative feedback. That is, output coming from the feedback is not helping the input. It is not being added to the input before being applied to the op-amp at this terminal. Okay. So it is a case of negative feedback here. In fact, we can talk a little bit about feedback before going further. Okay. So let us say we have a op-amp or any amplifier. Output is taken back via some feedback network to the input. Okay. So this is a feedback, and one can define negative and positive feedback. So for example, this is a case of negative feedback. So here the input that is being applied to this amplifier, okay, so this is not helped. In fact, this further reduces. So that is, feedback signal is subtracted from the input signal. Vin minus VFB is being applied to this amplifier. So it is a case of negative feedback. Similarly, if it is a case of positive feedback, so positive feedback out voltage, it helps the input voltage. That is, input voltage applied at the amplifier is now the sum of, this feedback signal adds to this input voltage, or it helps this input voltage. So final input is applied as Vin plus VFB plus feedback voltage. Yeah. So that is how one can identify the feedback in op-amp also. And in fact, in the op-amps, op-amps are generally used with negative feedbacks, right? So most op-amp circuits, they employ negative feedback only. Positive feedbacks are rarely used, only for oscillator applications. Okay. Mostly the op-amp circuits are based on negative feedback. Okay. So let us classify again the op-amp circuit. So if I have a op-amp circuit, it can be either closed loop or it can be open loop. We never use op-amp in open loop, always use it in closed loop. Okay. And if it is a closed loop or with feedback, then there could be a negative feedback, and also it could be a positive feedback. Okay. And most op-amp circuits employ negative feedback. Now let us do some more analysis before going into this op-amp. Okay. We had assumed that the ideal op-amp has an input impedance of infinite. Okay. So input impedance of infinite, so this also ensures that the current drawn by this amplifier will be 0. That is, current going from this terminal I1, so this is 0. Current going into the op-amp from this terminal, so this is also equal to 0. Okay. So one can say I is V by Z or R input. Okay. And if Ri is infinite, so obviously this is 0. So current drawn by this op-amp will be 0. That is, nothing goes inside this op-amp. Okay. So this is very important point to remember, that no current enters into op-amp because input impedance is infinite. Okay. Now the next important point to notice here is that the gain of this op-amp is infinite. Open loop gain is infinite. Okay. Or V naught by, that is the output, by the differential input. Okay. If V1 and V2 are the inputs, then differential value of these input is V1 minus V2. Okay. So this open loop gain is V naught by Vd. Okay. So V naught by Vd is also infinite. So I can write V naught by Vd is also infinite. Okay. Or from here I can write Vd as V naught by infinite, so which is 0. That is, this differential input Vd. Okay. That is this Vd, which is differential input V minus V2. So this is 0. Okay. So this would also mean that my V1 will be equal to V2. Okay, so if V1 is equal to V2, then only V1 minus V2 is 0. Okay, so this is another important property to remember, that in an op-amp these two terminals are at the same potential. Okay. So if I try to connect this to ground, so this potential will automatically be considered at ground or virtual grounded. So if I consider this to some battery 5 volts, or let us say 1 volt, so then that means this V1 will also be automatically at 1 volt. Okay, so that is because V1 is equal to V2. So why V1 is V2? Because my gain of this op amp is infinity. Okay, so these two things are important to remember. Okay, 1 and 2. Yeah, so since V1 is equal to V2, we had said, okay, so if I try to connect this terminal, a non-inverting terminal, to ground, so obviously this terminal will be at ground, or this is also called virtual ground, that is like ground. It is not physically connected, but because of this property, okay, V1 is V2, so the differential input should be 0. V1 minus V2 should be 0. So that would mean that this is also virtually grounded. Okay. So even if I am applying Vs over here, still this input is virtually grounded because the other input is grounded and nothing goes inside the op amp. Okay, I is 0 here inside. So we had said that one cannot use op amp in open loop configuration. So a practical op amp circuit will obviously contain a closed loop configuration, for example this. Okay. And in this closed loop configuration, by using these two resistances, if I connect my input at the non-inverting terminal, sorry, inverting terminal, right? So minus is inverting terminal. So if I connect this input V1 at the inverting terminal side, so this is called an inverting amplifier. Okay. So inverting amplifier, that is whatever you apply at the input, so that will be inverted, and at the output you will get an inverted version of this input. Okay. So for example, if you apply an input like this, at the output you will get an inverted output 180-degree out of phase. Okay. The magnitude may be large, but the phase would be different, that is 180-degree out of phase. Okay. Now we had written earlier that the gain of this amplifier can be written as minus RF by R1, that is the gain of this is controlled by these two resistances. So how? So for that we can use KVL. Okay. Let us say that I1 is going, okay, in this resistor, and since the current which is going into the op amp is 0, so that means the same I1 is going in feedback resistor also. So, and this node is at ground potential, virtual ground, okay, because the other terminal is grounded, that is this terminal is grounded, so that is why this terminal will also be at ground potential 0. So I can write KVL, that is Vi minus 0 is I1 R1, I can write. Okay. So let us write Vi minus, okay, 0, or V1 minus 0 is I1 times R1. Fine. Or from here I can directly write that I1 is V1 by R1. Okay. Now in this loop I can write, this is at 0, so 0 minus V0, okay, this is V0, 0 minus V0 is I1 times RF. I can write 0 minus V0 is I1 times RF. Okay. 0 minus V0 is this much. Okay. Or from here I can write V0 as minus I1 times RF, and I1 we had found here, which is V1 by R1. So I'll put this I1 here. So this V0 becomes minus V1 by R1 times RF, and if I bring this V1 down over here, okay, so this becomes V0 by V1, so which is minus RF by R1. So this is the gain of my this amplifier, which is equal to this value over here. Okay. So that is the gain of this operational amplifier is now controlled by these two resistances. Okay. So it is not infinite. Now open loop gain is infinite, okay, for ideal op amp, but closed loop gain, so this is controllable via feedback resistances, or maybe via resistances, I will call via resistances. Yes. Now similarly, if I try to connect input on the non-inverting terminal, right? So this is my non-inverting terminal. Okay. So if the input is connected at the non-inverting terminal, so then this becomes a non-inverting terminal amplifier. Okay. And this terminal has to be grounded, inverting. So here earlier I had connected input, so this is now connected to ground, and the input is connected to the non-inverting terminal. So this becomes a non-inverting amplifier, that is output will be in phase with the input. So whatever input I apply, so output will be in phase. It may have a larger magnitude, but phase will be same. Okay. And the gain of this amplifier can also be found. So before that, we need to decide the currents. Okay. So for this non-inverting amplifier, the current I, okay, through this feedback resistor, and then nothing goes into the op amp, and the same I comes into this R1. Okay. Now one can again write the using KVL. Okay. So now since this node is connected to V1, so that obviously means that this is also at the same potential. Okay. So earlier we had said that if this is connected to ground, so this is virtual ground. Okay. But now since this is connected to V1, so this is automatically connected to V1. Right? That is, at this node potential is V1. Okay. So I can write KVL knowing this is V1, this node is V0. Okay. So I can write here KVL, this is V1, so V1 minus 0, I can write V1 minus 0 is I R1, or I is V1 by R1. Okay. Similarly, for this loop, I can write V0 minus V1 is I times RF. V0 minus V1 is I times RF. Okay. And if I put I as V1 by R1 from here, so this becomes V0 minus V1 is V1 by R1 RF. And if I bring this V1 over here on this side, so this becomes V1 plus V1 RF by R1. And if I bring this V1 outside, okay, so this becomes V1 1 plus RF by R1. Okay. And if now I bring this V1 down here on the left hand side, so this becomes V0 by V1 is 1 plus RF by R1. Okay. So which is actually the gain of this amplifier. Okay. So V0 by V1 is the gain, closed loop gain, which is 1 plus RF by R1. So again it is controlled by these two resistances, the gain. Okay. So I think yeah, the same procedure we have over here, and the gain is the same, that is V0 is V1 1 plus RF by R1, or V0 by V1 is 1 plus RF by R1. Okay. Now let us consider a few examples. So let us say we want to find out the gain of this circuit, or maybe the output of this circuit. Vs is 10 millivolt, and since this is an inverting pair, so V0 by V1 will be minus RF by R1. RF is 10, R1 is 1K. You plug in all these values, you get gain output as minus 100 millivolts. Similarly, this is a non-inverting pair. So for this, V0 by V1 would be equal to 1 plus RF by R1. We have already calculated. RF and R1 are given to me. Okay, RF or R2. So one can find out the gain as 110 millivolts. Similarly, for this circuit, let us say that it's a inverting, because the input, which is 1 milliampere current, is connected to the inverting terminal, other is grounded, so it is inverting configuration, so output will also be negative. Okay. So one can say that since this node potential is at ground, so this is also at ground 0. Okay. Now one can write again using KVL. Okay. Current direction here 1 milliampere, the same 1 milliampere comes here through this 10k resistor, nothing goes inside the op-amp. Okay. So one can write 0 minus V naught is 10 multiplied by 1. Okay, 0 minus V naught is 10 multiplied by 1, or one can find V naught as minus 10 millivolts, 10 volts from here. Okay. Now if my op-amp is connected in this configuration, that is on the non-inverting terminal, input is applied and the inverting terminal is shorted to the output. Okay. So then this is called a voltage follower configuration, because here output will be equal to input. Okay. So because this node potential, which is V1, so that means this node potential will also be V1. Okay. That is, which is also equal to V naught, right? So we say that this is a voltage follower, that is whatever you apply at the input will be present at the output. So voltage follower using op-amp. Then using this op-amp one can also make a summing amplifier, that is, I want my output V naught to be equal to the sum of the inputs, adder or sum of the inputs, right? So this is true when all the resistances are equal, R1, R2, R3 and RF, all are equal, then this is true. Okay. So this can also be, I mean, KVL can be applied knowing that the current through R1 is I1, then I2 and I3, and these all currents I1 plus I2 plus I3, they go into RF as I. So I can be written, total I which is going through the feedback resistor is I1 plus I2 plus I3. Okay. And I1 can be written as V1 by R1. Okay. So one can write I1 as V1 by R1. Then similarly V2 by R2 is I2, I3 is V3 by R3, which is I. So which is I, that is this node is at 0. Okay. So that is 0 minus V naught is I times RF, or I is minus V naught by RF. So we can write I as minus V naught by RF. Okay. If I bring RF on the LHS left hand side, okay, so if I bring RF on the left hand side, then this would become RF by R1 V1 plus RF by R2 V2 plus RF by R3 V3. Okay. So this will be equal to now minus V naught, right? And if I say all resistances are equal, R1 is R2 is R3 is RF, then I can write that V naught, right? So all these are equal, so V naught can be written as, minus will come on the RHS, V1 plus V2 plus V3. That is, it acts as a summer. Okay. It's an inverting summer, but which produces an inverting output because negative is present over here at the output. Okay. Yeah. Okay. Yeah. So this is the same equation V naught that we have just now found. All resistances are equal, so this is minus of V naught plus V2 plus V3 output. Okay. Now let us take a design example. We want to design a circuit that will generate this output to these inputs. Okay. So the circuit I want to design which will generate this output to these three inputs, VS1, VS2, VS3. Okay. So for this I can use my summing amplifier, which we have already discussed here. Okay. So this can be utilized. Alright. So that is, this circuit can be utilized. We have three voltages, VS1, VS2, VS3 coming through these three resistances. So this is also a summer or a summing amplifier. So this can be utilized here to produce this output. Okay. We have to now decide R1, R2 and R3 because the output of this amplifier will be this much, which is, we have simply copied this equation. Okay. That is, this equation is also valid for the output of this circuit. Okay. So the output is of this circuit is this much. Okay. Now we have to decide RF by R1 because RF by R1 should be equal to minus 10 here, right? So I want RF by R1 to be equal to 10. So if I say that RF is 10 and R1 is 1K, okay, 10 by 1K, okay, so then this is produced, that is minus 10 Vs1. Similarly for minus 4 Vs2, I want this RF by R2 to be equal to 4. RF by R2 should be equal to 4, and RF we have already commented it as 10. Okay, so R2 can be fixed to 2.5K, so that RF by R2 is 4. So R2 can be fixed to 2.5K. Similarly, this term should be 5. That is RF by R3. So this should be 5. So RF by R3 should be 5. And RF we have already fixed to 10K. So R3 can be fixed to 2K. So to result into this term as 5. Okay. So that way one can design not just this output but any other output can be designed. Okay. Similarly, now let us say that we have another adder example. So this time the inputs are applied to the non-inverting terminal. So that means output will be positive in phase with these two inputs. Okay. So for finding out the output of this circuit, I'll again use the same relation, that is V0 is 1 plus RF by R1. Okay. So 1 plus RF by R1 if R1, R2, R3 are not present and only Vs1 is present, or maybe only Vs2 is present. Same relation I will use, but I will now apply superposition also, that is I will calculate the outputs with presence of single inputs at a time. Vs1 and Vs2 are present at a time. So I get output, let us say V01 and V02 here. The final output will be equal to V01 plus V02. Okay. So for finding out V01, okay, so in this case it is having just one input. So I can use this 1 plus RF by R1 V0 by Vin, this relation. Okay. Now I want to find out Vin for this circuit. Vin, that is input that is appearing over here at this point. Okay. So which will give me the gain of this circuit, V0 by Vin. So V0 by Vin should be 1 plus RF by R1. So I have to find out Vin over here. Okay. So then I can say V0 by Vin is, or V0 by V01 by Vin is 1 plus RF by R1. Okay. So for finding out the output, I need to find out Vin, that is input which is going into the op-amp here at this point. So for finding out the input at this point, I need to apply the voltage divider, because this Vs1, so this is dividing on the parallel combination of R2 and R3 and R1. So we can use voltage divider scheme to find out Vin. Okay. So Vin using voltage divider can be written as Vs1 times, it is dropping on R2 parallel to R3, divided by R2 parallel to R3 plus R1. Right. Similar to what we had done for a common emitter amplifier configuration with voltage divider biasing. Okay. So same way one can find out Vin1 at this point, Vin at this point, because in this equation V0 by Vin is 1 plus RF by R1. To find out V01 I need Vin, which is dropping at this point. So this is this much. Okay. So that is V01 can now be written as 1 plus RF by 1 multiplied by Vin. Vin is Vs1 R2 parallel to R3, okay, divided by R2 parallel to R3 plus R1. Okay. So I can write this V naught as V in times 1 plus RF by 1. V in is this much here. So this is same. And then 1 plus RF by R1 also comes over here. Similarly, I can find V naught 2 for this circuit, right? So this is my V naught 1 complete. So I can find V naught 2 for this circuit with Vs2. So again I'll find this V in here, so which is dropping across R1 and R3 in parallel. Okay. So I can write V in as Vs2 multiplied by R1 parallel to R3 divided by R1 parallel to R3 plus R2. Okay. So then again using this relation, so I can write VO2, right? So VO2 is V in multiplied by 1 plus RF by R4, right? So this is not V naught 1, this was V in also here. Let us say V in 1, V in 2, V in 1, V in 2. Okay. So one can find out the output voltage for this example, okay, by considering one input at a time, okay, using superposition. Okay. Now in this equation for output, we see it looks very complex, right? So this can be simplified if I can assume that my parallel combination of R1, R2 and R3 is Rp. So if I can assume this in this equation, then this can be modified or simplified to this relation. Okay. So this relation of output is now simplified to this, that is Rp by R1 Vs1, Rp by R2 Vs2 multiplied by 1 plus Rf by R4. Now similar to adder, one can also think of having a subtractor from the OPAMP. In fact, difference amplifier means the output is the differential output, that is if I apply, let us say, one input here as Vs1 on the inverting terminal, and on the other terminal non-inverting if I apply Vs2, so then output will also obviously depend upon the difference of these two inputs, that is Vs2 minus Vs1. Okay. So I can find out the output of this circuit, which is a subtractor using OPAMP. Okay. So for finding out the output, let us first of all find out the potential at this point. Okay. So potential at this point due to this Vs2 using the voltage divider would be Vs2 multiplied by R3 divided by R2 plus R3. So I can write V, that is this potential is Vs2 multiplied by R3 divided by R2 plus R3 using voltage divider. Now this potential should be also present at this point because these are virtually connected. Okay. So that means this potential will also be equal to this potential. So I can write that this potential is also Vs2 R3 by R2 plus R3, the same value. Okay. Now I can so now one can write, let us say, the current, the direction of current is, it is going into R1 and then the same current is going into RF. Okay, I know this node potential, so I can write KVL for this, that is Vs1 minus this node potential would be equal to I times R1. Okay, or I can write this I flowing, so I would be equal to Vs1 minus this node potential divided by R1. Okay, Vs1 minus this node potential, which is this much, divided by R1. Okay, same current now flows through RF also, that is this current I is also equal to the same value. Okay, all right. So we have found I, okay, and one can also found this I, which is flowing through feedback resistor by using KVL around this loop, that is this node potential minus this node potential V naught is equal to I times RF. or I is this node potential minus this node potential divided by RF. Okay, so I can write the current flowing through the feedback resistance as this node potential, which is Vs2 R3 by R2 plus R3 minus V0 divided by RF. Okay, so this I can write here, and we have so this I can write over here. Now using this and this, okay, I can further write this as this much. Okay, that is, I have now two relations, okay, and that is, one relation has V0 present and one is this relation. Now using these two relations I can write V0 finally as this much. Okay. Now this V0 contains Vs2 minus Vs1. Okay. That is, this will act as a subtractor, that is V0 will be equal to Vs2 minus Vs1 if all these resistances are equal. Okay. So let us say all these resistances are equal and R3 by R2 is much larger than 1. Okay. So then I can write the output voltage is the Vs2 minus Vn, that is, it acts as a subtractor here. Okay. Yes, so I can write, in fact one has to choose this R3 by R2 should be equal to Rf by R1 here. So then V0 will be equal to this much, and if Rf and R1 both are equal, then Vs2 minus Vn will be the output, or a subtractor output can be obtained. Okay. Now one can also think of having both adder and subtractor within the same circuit. Okay. So for example, in this circuit, this implements both adder and subtractor. Okay. Adder, that is adding these inputs Vs3 and Vs4. Okay. So Vs3 and Vs4 are added, that is Vs3 plus Vs4 we are seeing. Okay. Vs3 plus Vs4, and Vs2 and Vs1 are subtracted from Vs3 and Vs4. So Vs1 is subtracted minus, and Vs2. So this is also subtracted by this minus. Okay. So I can write a relationship here, that is V0 is this much. Right. So this we had seen earlier, the output, and this comes from the inverting inputs. Right. So these two comes from the inverting inputs, Vs2 and Vs1, and one which is showing in yellow, that is this one and this one. So this comes from the non-inverting output. Okay. So both adder and subtractor operation can be achieved in the same single circuit using OPAMP. Okay. Now one can also think of making an integrator circuit with OPAMP. So if I connect a capacitor instead of a feedback resistor here, so this circuit acts as an integrating circuit, that is, output will be equal to the integral of the input. Okay. That is, output is minus 1 by RC integral of Vt, V input. Okay. So that can again be found, this can be found by again writing the KVL around this OPAMP circuit. So one can write Vs minus, this is at 0, so Vs minus 0 is I times R, or I can be written, that is, this I can be written as Vs by R. Okay. And the same I is going into this capacitor, okay. And this I is also equal to, knowing that this is at 0 and this is as V0, so I can write this I is also equal to C dV by dt or minus C dV naught by dt. Okay. So that is, these two I currents are equal, so I can equate these two currents. So Vs by R is equal to minus C dV naught by dt. Okay. I take dt up over here, I integrate both sides, I get final output as integration of the input. Okay. So this can act as an integrator also. Now this circuit can also act, OPAMP can also be used to create a differentiator, okay, by replacing R1 by capacitor, and RF remains over here. So this acts as a capacitor, that differentiator, output will be equal to the differentiation of the input, that is V naught t output is minus RC d by dt of input. Okay. So again current can be written, this current I, so this is C dV S by dt, knowing this point is at 0, so Vs minus 0 is C dV S by dt, one can write, or I is C dV S by dt, and the same current is going into this, right, and this current can be written 0 minus V naught is IR, or I is minus V naught by R, and I is C dVs by dt also. So these two currents can be equated, okay? And from here one can find that the output voltage is minus RC dVs by dt, or this circuit acts as a differentiator. Okay. Now this circuit can also, we can also create a logarithmic amplifier using a OPAMP. So instead of using a resistor here, again in the feedback loop, if I connect a diode on the feedback loop, so this can work as a logarithmic amplifier. Okay, that is output will be equal to the log of the input. Okay, so let us try to again write KVL for this circuit to find out the final output V naught. Okay, so the current, again here this node I'll assume at 0 because this is grounded, so I can write this current I as Vs by R, okay, and the same current I Vs by R is going into this diode also, and for the diode current I can write this equation, current equation for the diode, that is I is Is time e to the power V by Vt minus 1. So that means this current and these two currents are equal. So if I equate these two currents over here, I get this relation. From here I can find V naught. Okay. So V naught one can found, so this is equal to Vt log 1 plus Vs by Rios, or maybe one can write that V naught is minus Vt times log of Vs by Rios. So it's again an inverting logarithmic amplifier. Minus is present over here, so this will come on the RHS. So a logarithmic amplifier can be created using an OPAMP. Now similarly an anti-logarithmic amplifier can be created by connecting diode here and feedback resistors remain same. So again the current through this can be written using the diode current equation. Same current flows through this resistor, knowing this node potential is 0, so 0 minus V naught, or maybe I can write I going through this is minus V naught by R. Okay. So both these two currents are equal, so I can equate these two currents, okay, and from here I can find V naught. So V naught is equal to minus RIS e to the power Vs by Vt, so which is anti-logarithmic operation. Okay. So anti-log amplifier can also be created using an OPAMP. In fact, many other configurations can be created. Now similarly, let us see a comparator using OPAMP. Okay. In fact, an OPAMP under open loop condition acts as a comparator. Okay. So how it acts as a comparator? Let us see. So we understand that the the output of this OPAMP can be maximum plus minus VCC. Okay, so that is, it will be saturated to plus minus VCC always. Okay, so OPAMP in the open loop acts as a comparator. How it acts as a comparator for that? Well, maybe before that, I think I have skipped some slide for. No, nothing is skipped. Okay, everything is intact, no issues. Okay, so OPAMP in open loop configuration can act as a comparator. Okay, so how, let us say that to the non-inverting terminal 5.5 volt is applied and here 5 volt is applied to inverting terminal, right? So what will be the output here in this case? Okay, so output, the maximum, if the gain is large, let us say we had assumed gain is 10 to the power 5, right? So V naught would be gain multiplied by the input, so that is 10 to the power 5 multiplied by input is 5.5 volts, right? So this cannot be achieved. In fact, if I try to amplify using this open loop configuration, the output will be clipped to plus 12 volts or minus 12 volts. Okay. So in this case, since the difference, that is VD, differential input is negative, minus 0.5 volt, that is VD is 5 minus 5.5. So this is 0.5 volt negative. Okay. So that is, the output should also be negative. Okay. So that means the difference that you are applying here, VI. Okay. So in fact I should write this as a differential input. Okay. So this V0 will be equal to open loop gain multiplied by differential input, which is V1 minus V2. AOL multiplied by V1 minus V2, differential input. Okay. And V1 minus V2 is minus 0.5 volts. So AOL multiplied by minus 0.5 volts. Okay. So the gain will be, in this case, clipped to minus 12 volts. Okay. Because we have applied an input on the non-inverting terminal which is greater than the input present in the non-inverting terminal. Inverting terminal, the input is larger, 5.5 is larger than 5 volt. 5.5 is present at inverting terminal and this is present at non-inverting terminal. So now this OPAMP in open loop configuration, it is acting as a comparator, that is, it is telling you which of these two inputs are larger. So if input applied at inverting terminal is larger, the output will be clipped to minus 12 volts. Similarly, if input at the non-inverting terminal is larger, the output will be clipped to plus 12 volts. Okay, so in this case the difference will be 5 minus 0, that is 5, so plus 5. So the output cannot be, I mean, if AOL is 10 to the power 5, so it cannot be 10 to the power 5, the gain cannot be 10 to the power 5. Okay, so it will be clipped to minus 12 volts here, and in this case it will be clipped to plus 12 volts, right? V0 is again 10 to the power 5 multiplied by 5 minus 0. Okay, so it cannot be this much, but since this itself is positive, so the gain, sorry, the output will also be positive and it will be saturated or clipped to plus 12, that is power supply. So this tells me that which input is greater. Okay, that is, it compares the inputs, and results in which input is larger. Okay. So it does a job of comparator. It compares these two input. If the input which is applied at the inverting terminal is large, then the output will be negative, clipped to power supply. If the input at the non-inverting terminal is large, the output will be clipped to plus 12 volts or plus VCC. Okay, so this is how it can act as a comparator in open loop. Comparator. Okay, so OPAMP, I'll write OPAMP in open loop. Okay, so this acts as a comparator. Now, knowing that the OPAMP acts as a comparator, I can find out the output of this circuit. Okay, so let us say that input applied is 1 volt sine 2 pi ft. Input frequency is 1 kilohertz. That is, this input is applied over here. Okay, so this is 1 volt sine 2 pi ft. Okay, now let us say that I have this circuit. Okay, so the output of this circuit, right? So this is a sinusoidal wave input. So let me draw this over here like this. Okay, the peak is 1 volt minus 1 volt. Okay, frequency is 1 kilohertz. Okay, so for this input VO1, that is output here. Okay, so this can be found by using that this compares the two signals. That is, when V in is large, okay, so V in is increasing or V in is large, so output will be clipped to plus 5 volts. So output is clipped to plus 5 volts when V in is positive. Similarly, when Vin is negative, output will be clipped to minus 5 volts. Output is clipped to minus 5 volt. So that is through this circuit, the output VO1 we achieve as a square wave or maybe a pulse, a square wave pulse, okay, of the same frequency as input. Now this is applied here at the input here to this op-amp. This is an integrator here. So whatever I apply, that is the output will be the integration of this square wave. Okay. Right. So the output of this circuit integrator is a triangular wave in response to the input, which is a square wave. Okay. So how this is a triangular wave? Okay. So one can understand from here that is this node is at 0, so this node should also be at 0, and VO1 I am applying 5 volt and minus volt. So let us say when this is constant 5 volts, okay, and this 5 volt, okay, for time period t, okay, it is 0.5 milliseconds. So for 0.5 milliseconds, if I apply plus 5 volts here, okay, for 0.5 milliseconds, so for that 0.5 milliseconds, my this op-amp, okay, this node will try to bring the input to 0 at this point, because this is virtual ground. Okay. So if I am applying plus 5 volt continuously for 0.5 milliseconds, for those 0.5 milliseconds, this node will try to push, this op-amp will try to push this node to 0. Okay. So that is the output of this op-amp will start falling for the entire region. When my output is plus 5 volt for 0.5 millisecond, this output will, this output and this output, right here, these two, so these will try to bring the output down, because this node has to be down, brought down to 0. So that is why I see that output is decreasing. Now similarly, when minus 5 volt is applied here, so again 0 volt has to be established here. So that means the output will try to increase to raise this potential to 0 from minus 5 volt. So the output is increasing, similarly decreasing, again increasing, and so on. Okay. Yeah, so I think I'm done with this portion on the basics of op-amp. Okay, so we'll carry on with a few more things on op-amp in the next lecture.